We're going to wrap this up, this idea of titrating and figuring out what the pH is at the equivalence point. So remember, in the titration, you've got two reactants, one in the burette, one in the beaker, and you stop adding the reactant in the burette the instant everything in the beaker reacts. Everything in the beaker's done, right? The reaction goes to completion. So there's nothing left. So in the beaker. So the idea is well, what's the pH at the equivalence point, which is kind of important because what pH are you going to end up with? Are you going to end up with an acidic or a basic solution, which is really important for no matter what process you're really talking about here. So we've done a lot of the work already, and we're going to see that getting our final answer, the pH at the equivalence point, is really just one last little step. But let's see if we can remind ourselves of a few things here. Gabby, we're titrating HCN with NaOH. And would it be a Ka or a Kb reaction that would really control the pH? A Kb, she's right. So Danielle, what Kb reaction would that be? What reaction would that be if you titrate HCN with NaOH? The Kb reaction that controls the pH. Whoa, just the reaction. Just the reaction. Right? Has to be a Kb reaction. Right? So we're HCN reacts with NaOH, you end up with the conjugate base. Right? Remember, this will always work. But this isn't what they want. Plus what, everybody? And this is the general Kb reaction. Plus H. Right? This is the general reaction. And this always works. When we're doing ice, this will always work. Except if you gave this as, if this was a quiz or a test question, this would be wrong because I want the exact reaction, not the general reaction. So what would the general reaction be? Now, Danielle, do you see what I'm after? Keep picking on you. Oh, not C, it has to be the conjugate base, though. Not HCN. It has to be CN with a minus. Perfect. Keep going. Yeah. Yeah. Perfect. Right? So that's what they want. How about if we titrate HF with NaOH, Sabina? What would be the reaction that would control the pH? What would it be? Remember, the one thing that helps me with this stuff, I don't know if it helps you, is if I am starting out with the conjugate acid, it has to react with a base, but I end up with the conjugate base. So that's one way to think about it. The other way to think about it is if you titrate with a base, you get a base. Do you notice that? If you titrate with an acid, you get an acid. So, I mean, it'll be the conjugate, but that's okay. So if you titrate with a base, you're going to have to write a Kb reaction. What Kb reaction would that be, Jasmine? Uh-huh. Yeah. And fluorine's negative. All right. Okay. Last one before we move on here. Alyssa, we're titrating methylamine with HCl. Will we be writing a Ka or a Kb reaction? Yeah, do you hear what she's talking about? Now, when she said that one's a base, what she's talking about is the methylamine. Now, how did she know this is a base? Yeah, there's two ways. I'd say one is you titrate it with HCl. So you know it has to be a base. That's one way. The other way is you could just find it in the chart, the base table, right? But I think this one's kind of easier. But if you have to write the reaction, you got to know what the formula is. So that's why I give you the table. Now she's right. You're going to have to write a Ka reaction, Erica. She's right. What Ka reaction would you write? What's the general formula? Let's start with that first. Let's ask you that one. Erica, what's the general formula for a Ka reaction? Well, no, wait, except we don't call it HCN. We're calling it HA. Yeah. Yeah. Perfect. That's the format this has to be in, right? So let's see if Tegan can tell us what's going on here. So that format, Tegan. Okay, now she grabbed the CH3NH2. Now is that right? Does everybody agree? You have to put an H in front. So either put an H in front or make that an NH3. Either one would work. So we got to make that the conjugate acid. Okay, keep going, Tegan. Good. Then yielding H plus. Perfect. Okay. So it is of this form, though. I think this helps. Okay. So today we're just going to go full circle. We're going to do everything we did the last class, and then we're going to figure out the pH. We're just going to do ice, though. It's not too bad. So we have 12 grams of acetic acid, and we're dissolving it in 50 mils of water. We're titrating it with 2.8 molar NaOH. At the equivalence point, Diana, which one will dominate, the acetic acid or the acetate? Which one would dominate? What do you have? Do you agree? She says it's this one. Daisy, you agree? Right? We're starting out with, which one are we starting out with? We're starting with it with the acetic acid. We're starting with this one. All right? Right, we're starting with it. And then it reacts with the NaOH. Yeah, so it's all gone. She's right. It's all, you end up with a conjugate base. Right? Titrate with a base, you get a base. Okay. Ellison, now we have to figure out the concentration of this acetate. If I want to use all my right notation, I'd probably write something like this. But concentration, remember, Allison, what's the starting point for doing this? Where's Allison? What's the starting point? Molarity. And that was what over what? Moles over liters. Exactly. Okay, which one do you want to do here? Crystal. Where'd she go? Crystal? Yeah. Crystal Zamora. Yeah, so we have to find both of these. We have to find moles, we have to find liters. Now, one of them is going to be a lot easier than the other one. But
You start with liters.
Oh, don't start with that one.
No?
Because that one, do you see why that one's so ugly? Does everyone see why that one's so ugly? Because if you calculate the liters, it's deceiving. Because it looks like Yeah, she said, you're right, grams per mole. But I just want to finish this story. It looks like you'd have 0.05 liters. But we added a bunch of NaOH. So you have to add some liters. So that one, it's going to be a little job. And it's easier to do the liters if you do the top one first. And she's right. Do you hear what she said in getting the moles? Let's see if Crystal Munoz, did you hear what she said? How is she going to get those moles? You didn't hear what she said. Did anyone hear it? Daisy? Grams to moles. How do you go from grams to moles? What was the word? Molar mass. Right? We've got 12 grams. Right? We need the molar mass of this stuff. Drakesa, how do you get molar mass again? We just want molar mass, right?
Oh, okay.
So
you take that one, you divide it by the grams.
yeah, I have to add it all up.
Yeah.
Are we adding it up for the C2H3O2, or are we adding up the formula for the C2H3O2? The H, because it's 12 grams of acetic acid. So we've got how many grams of HC2H3O2 in a mole of HC2H3O2? We've got, 4 hydrogens, 2 carbons. That's what, 28 and 32. That's 60, maybe? It is 60. 60. Okay. So we'll take, Tariq, give me my calculator back. All right, okay. 12 over 60. What'd you get? 0.2. Okay, so that goes right here. You have 0.2 moles. So the denominator needs liters. How do we get the liters? Danny, what would you do now? Right? How are you going to get this part? How do we get this equivalence point? Right? 'Cause we have to add so much NaOH to get it all to react. Okay, there. Okay, this is where it gets confusing. She said she's starting here, 0.05 liters. But that's 50 mils. That's not 50 mils of NaOH solution. That's 50 mils of water. So you can't take that 0.05 liters times the 2.8 moles per liter and get moles. That won't work. We need a different starting point. That will not work. The reaction. The whole point of the equivalence point is we know the moles of acetic acid. Well, that means you had to add how many moles of NaOH? Melissa, what? Say it. You're right. Say it.
I want to know.
Yes, you had 0.2 moles of acetic acid. So how many moles of NaOH did you have to add? 0.2. They have to be the same, right? They have to be exactly the same. That's the whole idea of the titration. So that's where you start. You could start with 0.2 moles of acetic acid or moles of NaOH. They got to be the same thing. I'm just going to start with the acetic acid just so I don't skip anything. But now it's what bridge? Mole bridge. And the mole bridge in these problems is always what to what? Yeah, always 1 to 1. Because in all of these acids that we're using, they're all in Greek. How do you say 1? The number 1? They're all what protic? Monoprotic, right? They're all monoprotic. So that all these reactions are going to be 1 to 1. Okay. We're not in liters yet. We want liters of this NaOH solution. but we're darn close. Vivian, what are we missing? Right? To get liters of NaOH. Somebody see it? We don't want to go to molar. We don't want molar mass because that'll give us grams. We want liter. We could, but molarity. All right. So how are we going to write it? 1 liter over 2.8. Exactly. Right. Now, where did Diana get that? Yeah, the moles per liter of the NaOH. She just flipped it. It's right here. She just flipped it is all. And now we can quit. Okay, Drake, so keep going here. You have my calculator. 0.2 divided by 2.8. 0.0714. Okay, so that has to go right here. Okay, now you gotta add it to 0.05, divide it into 0.2, Drake, so now what do you get? Daisy got 1.65. So did Jasmine. 1.6. Several folks got 1.65 as the final answer. I bet you that's right.
What are you supposed to? Oh, yeah, sir. You add it to 50?
0.05 because it has to be in liters.
Oh, because we got liters.
Yeah, so they had 50 mils of water in the first place, so we had to include that in the volume. And then we dumped in 71.4 milliliters, or 0.0714 liters of the NaOH. So you have to add that to the total volume. So add those two up, divide it into 0.2 moles, and you'll have the concentration. And hopefully you get 1.65.
And then the concentration is 1.65 M2C2H2O2.
Yeah, we should probably finish that. Would look better, wouldn't it? It's 1.65 molar acetate. So the last step here, to wrap it up, find the pH at the equivalence point. So step 1 we already did. I think that's the hardest part. Determine the concentration. Okay, and now step 2 and step 3, this is homework from, I don't know, 3 days ago, except they gave us the concentration. They said, okay, you have 1.65 molar acetate. What's the pH? Well, you had to write a K what reaction? KB, because it's an acetate, it's a conjugate base. You had to write KB reaction, and then do what? Do ice. That's all we're going to do. And that's what this thing says. Write the appropriate KB reaction. Okay, we'll do that. And then we'll do ice. Okay, so we need a KB reaction. What appropriate Gabby KB reaction would you write? Uh-huh. Yep, plus OH negative. And she just forgot the what? Do you see it? One little sign on something. The negative on the acetate. But notice that really doesn't affect your ice table, but okay, now I have to do ice. So Sabina, let's see if you remember how to fill out an ice table here. What did you do? Bless you. So all we have is this acetate. We calculated the concentration. Where did that number usually go? Yeah. In the initial row under it, right? So what number do I put there? 1.65. And then for water, so we didn't get confused, Jasmine, remember what I suggested? Just do what in the whole table for water? Put dashes. Otherwise, you end up doing X's or some crazy thing. We don't have anything initial for acetic acid or hydroxide. The change row, Alyssa, what did we do again? Negative X. Uh-huh. And then we subtracted them to get our equilibrium answers. Okay. Erica, then what do we do? The whole idea is to get pH. When we do get our X, that won't be that'll be the concentration of what? OH negative. So then, you remember the easy way to do this to get pH? Take the log of the hydroxide, you get POH and subtract from 14. So that's the big game plan. But what should we do now here, Tegan, to get that X? Okay, she says use the 1.7 times 10 to the negative fifth. She's talking about this. Use that for what? For the Ka. Okay. Because we need, you said Ka is 1.7 times 10 negative fifth. But still, what do you do though?
Set that equal to x squared over 1.65.
Okay. Now, do you see where she screwed up? She's close. Yeah, you got to find the Kb, because this is the K what reaction? Kb. So how do you get Kb again? Yeah, Kw is Ka times Kb. That's the one thing she messed up on. So my Kb is Kw divided by Ka. So I gotta move that down. 1 times 10 to the negative 14 all over 1.7 times 10 to the negative 5. Okay. 5.88 times 10 to the negative 10? Okay, let's see if Diana, when you see this Kb number, did you get this? 5.88 times 10 negative 10? Okay, when you see this number, Kb number 5.88 times 10 negative 10, what do you really like about it? We can drop the X. Why? You're right. But what do you look at to tell that we can drop the X? I don't know where the 1.65 you're coming from. That exponent had to be 10 to the negative, if you want to drop the X, 10 to the negative 4, negative 5, negative 6, right? Negative 6, and smaller and smaller and smaller. So that's what you should be happy about. You can definitely drop your X's. So go ahead and drop it. Calculate your pH. So you should be multiplying it by 1.65, right? Taking the square root, and then log it. And then whatever you get, subtract from 14. Now realize when you log it, you get a negative number, so you could really just add it to 14. Crystal, you got an answer? 9.5. Now I don't know if it's right or not, but I like the answer because the solution had better be what? Had better be basic. And that's a basic answer. So, Danielle, did you get 9.5? Tegan, got 9.5? All right, so 9.5? At least 3 or 4. Yeah, it's got to be 9.5. Can't do a check mark. Okay. Good. So if you got 9.5, go on to this next one. And I gave you the answer, the final answer. If you didn't get it, just let me help you out. So that equals that. So you take this times and then take the square root. So try it. That should be 5.88, right? Yeah. Yeah, and then square root. Okay, now that is your x. Take the log of it, and you'll have POH. But it's really, your POH is really 4.5. But it already has a negative sign down there, so just add it to 14. Yeah. So in this titration in EX3, realize we already wrote down the reaction. So you could pretty much just copy it over. Where did it go? There it is. And we're get you that table because I don't think this is a recent addition. Methylamine Kb is 4.4 times 10 to the negative 4. Let me write that down somewhere. For methylamine. That way you don't need the table. Oh, we forgot our arrow. So in this one, when you get your x, we'll just take the negative log of it and we quit, right? Because x is hydrogen ion. So don't do any subtracting from 14 for this one.
To find the thing, or we just use the KB?
So we have to find the initial concentration, and then we'll fill in the ice table. So you can start with the ice table because you know that's going to be the answer, but it's going to be a lot of work to get that initial concentration. You got to get this first. 4.4 times 10 negative 4. All right, so first you got to find it. Remember that's moles over liters. See what to do. So So then the moles part would just be, they gave you volume and concentration. So the moles of this methylamine has to equal the moles of this stuff, has to equal the moles of this stuff, because that's what the equivalence point would give you. So let's see if you're getting this here. Right here. All right, because you know the volume and the concentration of that methylamine. To get the volume in liters and multiply it times the concentration, you'll have the moles. The nice thing about equivalence point, all those moles are equal. That's when you quit. The conjugate acid, the conjugate base, the HCl.
For that, we have to find the equivalence point first, right? Or
It really doesn't matter which one you find first. Sometimes it's easier, I think, if you find this one first, but it really doesn't matter. It's really less work if you find this one first, because then you can use those moles and the mole bridge and convert to liters of HCl, but it really doesn't matter. It really doesn't matter. It's the same amount of work. Okay, so now you do ice, exactly. And you need to know the Ka, so Ka equals, you finish your ice table, and then be products over reactants. No, we don't put dashes for H. We put a dash for its initial concentration. So, Jerixa, I need my calculator.
Oh, it's at 9.8 times 10 to the negative.
For the moles?
Yeah.
Well, here, then you can just tell me this stuff.
What?
Okay, I think I saw Jasmine's. She got 0.12 molar for the initial concentration too, I think, right? All right, so good. So 0.12 should be in your table for the initial concentration.
Were you supposed to use the KA?
Yeah, look at the reaction. Is it a Ka reaction or a Kb reaction? It's a Ka reaction, so you have to use Ka.
You know, that yellow just doesn't really even.
So we're going to have to calculate it. So we're going to have to calculate it.
That's just too much.
You took my calculator again. Jeez. Well, that's okay. You can tell me. What did you get for your Ka number? 2.27 times 10 to the negative 11. And that has to be approximately x squared all over 0.12. So if you get the right answer of 5.8, just go on to the next one. But yeah, and then square root.
Dividing.
No, it's on the bottom. So you got to bring it up.
And square root.
Yep. What'd you get? 1.65 times 10 to the negative 6. And remember, X is your hydrogen ion concentration. So pH is, what'd you get, 5.8? 5.78? So Daisy, did you get 5.8 too?
Yeah.
Excellent. We have a couple minutes left to see if you have any questions. Now's the time to ask. How we went from one step to the other, or
Okay, so then once you have your H base, you put into a log.
yeah, because pH is negative all the way. And the reason why you know X is H is right here. X is H plus.